So we're now going to look at the different characteristics that define life and homeostasis and look at what homeostasis is. So movement, responsiveness, growth, reproduction, respiration, and digestion. These are the 6 different characteristics of life. You need to know this list and what they are, and you need to understand what they are. We are living organisms, and as living organisms, we respond to changes that occur in our environment. All organisms respond to changes in their environment, and an organism's main goal in life, if you wanted it to have a goal in life, is to survive and to reproduce. Survival and reproduction. Get their DNA passed on to the next generation. So as we're going through that, we are going to take in and break down food, and then we're going to assimilate and absorb that food in order to gain energy. We're going to use that energy in respiration for different processes like growth and repair. So let's briefly look at these words. Movement, of course, you understand that is a change in position. It is motion. So organisms that are living have some type of motion. They have responsiveness. They will react in some manner to a change. And on a very simple organism level, sometimes that is just chemotaxis, a response to a certain chemical and they move away, or phototaxis, where something will move away from light. With an organism as complex as ourselves, that responsiveness is much, much more complex. And then we also have growth. That can mean an increase in body size without a change in shape. Then we have reproduction, and of course that is passing on our DNA into future generations, right? Making new organisms and new cells. Then we have respiration, like cellular respiration, which we're going to look at in detail. This is where we're going to obtain oxygen, remove carbon dioxide, release energy from foods. And then, of course, we've got to do something with that. We've got to break down these molecules in our food substances into simpler forms that we can use. So some more characteristics of life are going to be absorption, which we kind of included a little bit with digestion. But once we break it down, we then have to assimilate it into our body and send it to the right area that it needs to be used. We're going to have circulation. And so if we have oxygen, we breathe it into our lungs, and then we have to circulate that to every cell in the body. We've got to have oxygen. So we have to have a way to send things like hormones, oxygens, and nutrients to different organs and organ systems in the body. Assimilation, I've already discussed that a little bit, but that's taking those substances into a different chemical form after it's been broken down that the body can use, and then we'll use that circulation to get it where it needs to go. And then we do have some waste. So we have excretion, that's removal of waste, and that is produced by metabolic reactions. And I'm just going to say, if you hear some snoring, that is my dog snoring. She's asleep in here. I am recording this at home because we are still at home due to COVID. And if you've watched this, I'm probably going to keep these in years later. Obviously, that wouldn't be this year if this is much later on. But anyway, if you hear the snoring, that is my dog. She's snoring. So all of these are physiological events that are going to obtain, release, and use energy. And we call that our metabolism. Okay. So our metabolism, if you were to define metabolism, in fact, I want you to pause the video as soon as I say this and tell me what is metabolism in your own words. Most people are going to say it is how we gain or lose weight. And it is definitely tied to that. But it's way much more complex with that. We're going to look at metabolism in depth. But it's not going to be the everyday connotation of the word that we use for metabolism. It's going to be the true scientific technical term. So when we talk about scientifically what metabolism is, that is all of the chemical reactions in an organism that are needed to maintain and support life. So metabolism is very important, and we're going to look at that in great detail. So if I were to ask you what you needed to live, you would give me 3 things, right? You need food, you need water, and you need some kind of shelter from extreme environments, right? Well, there's really actually 5 different things that we need. We do have to have water. We need food to survive. And we definitely, and you probably would have said this earlier, need oxygen. We cannot survive very long without oxygen, okay? I've heard people say the rule of 3 is 3 minutes for oxygen, 3 days for water, and food is really kind of that one you really can't just go with 3 weeks or 3 months. It really kind of depends on how much fat and muscle you have on your body for your body to break down, because your body will break down and use it. But there are 5 things that we need. So we also need heat, because without heat we would definitely freeze to death. And then pressure, and what we're talking about is atmospheric pressure, but we're also talking about hydrostatic pressure. What is hydrostatic pressure? Hydro. What is hydro? What do you think of when you hear the word hydro? I bet you're thinking water. You hydrate. Hydro. It does. It's referring to water. So water pressure, and what that is directly related to medically is things like your blood pressure. Because you know, or you should know if you work in the field of medicine at all, and if you don't, you probably are still aware that if you have no blood pressure, you can't sustain life, because you can't get oxygen or water where it needs to go without a blood pressure. So that's very, very important, that hydrostatic pressure. So let's break these down a little bit. We're going to look at them one by one. So we're going to start with water. Water, all of our chemical reactions in our body occur in water. So roughly 60 to 80% of our body is water. It is the most abundant substance in the body, definitely required for those chemical reactions for metabolic processes. It helps get things like hormones, oxygen, proteins, and things, ions, things where they need to go. And it actually helps regulate your body temperature. You're probably thinking of sweating, which is very important, and that is one of the ways, but there are other ways that we'll look at later on. Food is another requirement, okay? So we have to eat, and there's a lovely cheeseburger there on the screen. That is going to provide us with nutrients that we need to fuel our body. It provides energy and then raw materials we need in order to build, because we are constantly breaking things down and building things. Our major source of fuel is generally from carbohydrates. All right, so let's look at the other 3. We've got oxygen. Oxygen is a gas. It is in the air. When I ask the question, what is the most abundant thing in the atmosphere, most people want to say oxygen, and that's not true. It's really actually nitrogen. Our atmosphere is about 90% nitrogen gas. It's about 1/5. It composes about 1/5 of what the air is made of. We need oxygen, of course, for chemical reactions to occur. And you're going to see that we need oxygen for the most important chemical reaction in our body, or I say it's the most important, cellular respiration, because we could not maintain life without cellular respiration. So about 20% of the air we breathe is in the form of oxygen. We've got to have heat. Heat is a form of energy. Ultimately, all energy and all heat comes from the sun. Plants and those primary producers help metabolize that and put it into a form that we can use. Heat is also a product of metabolism, so that is why we have a certain temperature range for our body. We are producing heat all the time. Heat can actually help speed up a metabolic reaction, and you want to remember that temperature is actually just a measure of the amount of heat. Pressure is force divided by unit of area. So if we're talking about things like blood pressures, we're talking about the amount of force that is being applied to the area of the blood vessel. So this is really important to understand. There's also an application on breathing. Atmospheric pressure, when we breathe, we don't suck in air. It actually moves because of a difference in pressure, and we'll look at that in depth more in anatomy too. But it is related to expanding our chest cavity, increasing volume, decreasing pressure, and changes or a difference in the pressure in our lungs with that of the atmosphere. And that's what helps to regulate what goes in and what goes out. Homeostasis is a very important concept to understand in the body. This is how our body regulates almost everything, and it's very important, and it does so almost automatically. When we have problems and diseases, it is often caused by a problem somewhere in this chain of homeostatic mechanisms. Okay, we have these control mechanisms that regulate body temperature, that regulate different hormones in our body, that regulate sugar and the release of sugar in our body. And it's very, very important to understand. Now more than ever, our environment is constantly changing. And when I say environment, we can even look at the actual climate, because we have had very erratic weather the last few years due to things like climate change. And so we have to be able to respond to that in order to survive. We want to maintain a constant internal environment. You want your body functions to stay in their range. They have a very narrow range. Things like temperature, we have a very range of temperature, pH, how much water, how many water balance that we need. Like we said, glucose is also important. We need to keep those in a set range. We have these homeostatic control mechanisms, which basically act kind of like thermostats. And that keeps our body's internal environment at what we call a set level, at the set point. There are three parts to a homeostatic control mechanism. One is going to be the receptor. Receptors provide information about specific conditions. Is it hot outside? Is it cold? It also tells us about specific conditions in the internal environment, like, do you have enough blood sugar for your body to function? Do you need to increase that? Is there too much? Do we need to go and store that? All right. This is generally going to be something like a molecule or a cell that is going to act as a receptor. And then we have the control center, and this is where the set point is. That's a particular value, which for temperature is going to be like about 98.6. Okay. So we have a set point or a set area that we want to keep things in. So it's basically a lot like your thermostat, and we'll get into that in a moment. And then the last part is going to be that we have an effector. And this is what causes the change to return your set points, to return your whatever is out of line back to the set point, okay? This is often going to be the muscle or gland, and this is going to cause that change in the internal environment. That's what an effector is. So these are very important, very good understanding is needed in this concept to understand disease processes and when things go awry. Okay, so let's elaborate on this a little bit more, all right? How does this homeostatic control mechanism work? Receptors, again, measure those deviations from set point. You know, if you get too far from set point, and it's a range, it's not just one number. If you're 98.6, you don't automatically start sweating at 98.7, right? You have to get pretty hot before you start sweating. Effectors then are activated, and those are going to help return things back to normal, okay? And then receptors, they're going to go to the control center. Sorry, I skipped that one. That's where the change is compared, and basically the instructions are sent to the effectors to change it back. And then the response causes you to correct, and you get back to the normal internal environment. This is what we call negative feedback. We have two types of feedback, negative feedback and positive feedback, and I'll elaborate on those in a moment. But right now you need to know this is negative feedback. Most things in the body work on negative feedback. And negative doesn't carry a bad connotation here. It doesn't mean like, ooh, negative is bad or something's missing. It means you are returning things back towards the set point. Positive feedback is going to move them further away. So it makes sense that if we are trying to maintain a constant internal environment, that negative feedback, returning things back to normal, is how most things in our body are going to function, okay? So here's an example for you that really is a great illustration. If you have central heating and air, and you set it at, say, 70 degrees in your house, all right, whatever you're comfortable with. So if we set it to 70, that's the set point, okay? That is the set point. Now, if it is 70.1, it doesn't automatically kick on, right? It's got to go up a little higher than that. So it's going to have a little bit of a range there. So if it is hot outside and it gets up to, I think it's 2 degrees before the AC will kick on. So it gets up to 72, then it's out of range. And so then it's going to tell the control center, which is your actual thermostat. All right, so you had your receptor that detected what temperature is it in the house, okay? And then that is going to tell the control center, hey, we are above 72. We need to fix things to get back to set point. And then so that control center, that thermostat, is going to then send a message on to the compressor to kick on and turn the air conditioner on. And it is going to stay on. So the air conditioner part of the compressor, that is going to be the effector. That's the one causing the change. It is going to bring the temperature back down closer to normal. And so once it gets back down to closer to normal, the receptor is then again going to sense that and say, hey, we're 69.5 or we're 70. We can stop cooling things off now. We're going to get too cold. So it tells the control center, and then the control center tells the compressor to go ahead and shut off. Okay. And then let's say it gets really cold outside, and we've had weeks like that where it gets hot and cold within a period of days. So let's say it drops down below 68. It drops down below 68, the receptor is going to sense that or detect the temperature. The thermometer is going to measure that change in the internal environment in the house. And so then it's going to send a signal to the control center and say, hey, it's getting too cold. It's getting too cold. And so then that control center realizes, hey, this is below the set point. 68 is too far below 70, so it's going to send a signal to a different effector, which in this case would be the heat to kick on, all right? The heat to kick on. And so the heat will kick on. It's going to cause that response for things to begin warming up. The receptors will sense that, and when it gets back into the range, and it usually lets it go just a hair above, so it'll settle back down to normal, then it will tell the control center, hey, we've reached set point, and the set point will go to the effector and say it's time to stop. You can look at this really, really well when we talk about maintaining body temperature, okay? Maintaining body temperature. So if you look at this example, you get really, really hot, what happens? Think about that. What happens when you get really, really hot? Well, you're going to sweat, right? And so you're going to, your body is going to sense that your internal environment is above that 98.6, and it's going to tell the control center we're getting too hot, and so that is going to cause you to sweat. Then due to evaporative cooling, the sweat is going to help cool your body down. The receptors are going to, again, sense that, tell the control center you're cool enough, and so it will tell the sweat glands, in this case, to stop producing sweat, and you will go back to your normal set point. Then if you were to go out and it's very, very cold outside, your receptors, you have special receptors for temperature. You have some for heat and some for cold, so they're actually different receptors. But you will sense that it is cold. The receptors will say, hey, your body is dropping below the set point. So the control center will then tell the effectors, which in this case will be muscles. What happens when you get cold? You begin to shiver. So your muscles will begin to contract and shiver to warm your body up. Then your receptors will sense that, tell the control center you're warm enough, and you will stop. Okay? And you may be wondering, well, why do we get cold chills with fevers? Well, we're going to get to that in a whole different unit because that's really quite interesting explanation. But I'm going to leave that for later, so I'm going to make you wonder about that for a while. Okay? So I already mentioned that there are two types of feedback. Negative feedback, which is the one we just discussed, which returns us to closer to the set point. This is very important for you to understand the difference between these two. Negative feedback will return you to the set point, closer to where you want to be. Positive feedback actually moves you further away. And this is why there's not a whole lot of positive feedback that goes on in your body. One of the best explanations for positive feedback, remember that's moving something further away from your set point, is childbirth. All right. And so as you go into labor and you're going to have a baby, what happens? Well, you begin to have contractions. Well, the contractions begin to move the baby along through the birth canal and to press up against the cervix. All right. The cervix has sensors in it that receive that message, that act as receptors, and they send a message to the control center that says, oh, something's going on here. We need to make this go more. And so what happens? Your contractions get harder and faster. And then so they apply more pressure to the cervix, which triggers more increases in contractions, and it will ramp you further and further away and increase this event until something large occurs, like having the baby, which will cause them to then slow down and stop. You will stop having that pressure being applied to the cervix. You will still have some contractions, of course, afterward, which are really important, but you will no longer have that stimulus that is causing it. So that is the best example to remember. There are other examples, but that's one that we can all relate to and understand. But what you really need to be sure with these two things and make sure that you remember, negative feedback is what most of the systems in the body do, and that is returning things to that set point to help maintain a constant internal environment. And positive feedback is going to move it further away from the set point until the stimulus stops. All right? Very important to understand that. So this is a good summary slide here of negative feedback. This is going to prevent sudden, severe changes in the body. If your temperature gets too hot, that is very serious, right? If your temperature goes above 108, you're going to start to have some brain damage. Okay, so it's very important that we're able to regulate that. If it gets too cold, same thing. It's just not compatible with life. It's going to correct and move things closer to the set point. And this is going to cause the opposite of disruptions to your body. Okay, so the negative, that's kind of where the negative portion comes from. And again, this is the most important type of feedback loop. We discussed body temperature regulation is one. Blood pressure regulation and glucose regulation are also other examples of negative feedback. So here is that summary here of the childbirth example here. In positive feedback, the changes aren't reversed. They're moving closer to a set point. They're actually increased, remember, and moved further away from the set point until the stimulus is stopped. The effector is going to be increased instead of being turned off. So we talked about pressure for childbirth. We also have hormones that are going to intensify, and that's going to cause those uterine contractions, the strength of those to increase until childbirth occurs. The first contractions of labor act as the stimulus. That's going to push that baby towards that cervix, we said, which is the lower part of the uterus. And those actually have stretch-sensitive nerve cells that can actually feel that pressure, which is really pretty cool, and monitor that degree of stretching. And then that's going to send messages to the pituitary gland, which is at the base of the brain, which is going to release a hormone called oxytocin. That's going to go into the bloodstream, cause those stronger contractions of your smooth muscles in your uterus, which is going to push that baby further down, cause greater stretching of the cervix, more oxytocin release, more forceful contractions. You can see how this just is going to keep ramping up and cycling up. So stretching of the cervix then at some point is going to stop, and then the release of oxytocin will stop, and so forth. Blood clotting is a good example of this as well, because you do need to clot in order to stop bleeding, but you do not want that to continue on forever, okay? But it's not something that occurs all the time. So this is going to be more isolated incidences that you see with positive feedback. All right, it doesn't work very well to view these animations when you're recording a PowerPoint, so I'm going to put links to these for you to be able to watch them. This is a really good example. It will talk about some hormones and things that might go a little above your head right now, but they will be very important for you to hear, and it's going to give you some background information to help you understand when we get to these later on. Okay, so please do be sure and watch this animation, and that does it for this section.